Close your eyes for a moment and picture a sky with two suns in it. One hangs yellow-white and familiar, almost the colour of our own. The other burns orange off to the side, throwing a second set of faint shadows across the ground beneath your feet. This is not a painting, and it is not a film. It is the kind of sky you might stand under at the nearest star system to our own, just 4.5 light-years away, where the most powerful telescope ever built recently caught the faint warmth of something that should not have been visible at all. A possible world beside a star almost identical to the Sun, and then, only months later, it was gone. So what is hiding in the glare of our closest neighbour, and why will it not let us look at it twice? Make yourself comfortable and settle in. Subscribe if you haven't already, so you can be here when the answer finally arrives. Stay with us, because what this one vanishing world hints about planets around other suns reaches far beyond a single star. Let's begin. Part 1. The Cosmic Front Porch. There is a single point of light low in the southern sky that almost no one looks at twice. From the right latitude, on a clear night, it sits in the constellation Centaurus, yellow-white and steady, one more star among thousands. You would never guess, looking at it, that you are looking at the nearest doorway out of our entire solar system. You would never guess that the light entering your eyes tonight left that star a little over 4 years ago, travelled across an emptiness so wide that the fastest thing in the universe needed all that time to cross it, and arrived, finally, here, on your retina, at the speed of light and not one bit faster. That point of light is Alpha Centauri. It is the closest stellar system to our own, and for most of human history it is kept a secret that we have only just begun to pry loose. The number that matters is 4.37 light-years. That is the distance from Earth to Alpha Centauri, and in the language of the cosmos it is practically nothing. It is the front porch. Most of the planets we have discovered around other stars orbit suns that lie hundreds or thousands of light-years away, so far that the light we study left them before there were cities on Earth. Alpha Centauri is different. A photon leaving that system when a child starts kindergarten arrives before that child finishes the 4th grade. In a universe measured in millions and billions of years, 4.5 years is the blink of an eye. If the galaxy were a country, Alpha Centauri would be the house next door. For more than 70 years, astronomers have stood on that porch and asked one question, over and over, with a kind of longing that is hard to overstate. Does it have planets? It seems like such a simple thing to want to know. We can see the star. We have telescopes that have found nearly 6,000 worlds orbiting other suns. Surely the closest star system of all would give up its planets first. Surely the one place we might actually reach someday would be the easiest to study. That was the assumption, and it was wrong in a way that turned out to be one of the strangest and most beautiful problems in modern astronomy. Alpha Centauri is not one star. It is 3, bound together by gravity into a single family. The brightest member, Alpha Centauri A, is so similar to our own Sun that if you set the two side by side you would struggle to tell them apart. It has nearly the same mass, almost exactly the same size, a surface temperature within a couple hundred degrees of the Sun's, and roughly the same age, somewhere near 5 billion years old. It is, in nearly every measurable way, a twin of the star that gives us daylight. Its companion, Alpha Centauri B, is a slightly smaller, cooler, orange star, and the two of them circle each other in a slow waltz that takes about 80 years to complete one turn. And far out beyond them, drifting at a distance so enormous it staggers the imagination, there is a third member, a dim red ember called Proxima Centauri, the actual closest individual star to the Sun, so faint you cannot see it without a telescope. Think about what it would mean to find a planet around Alpha Centauri A specifically. We already know that the dim red dwarf Proxima has worlds of its own. Astronomers have confirmed at least 2 planets circling it, with a possible third still under investigation, but Proxima is a red dwarf, a fundamentally different kind of star from our Sun. Planets around red dwarfs live hard lives. They are bombarded by violent flares that can tear away their atmospheres. They huddle so close to their dim parent star that they often become locked in place, one face baking in eternal daylight while the other freezes in endless night. A planet around Proxima is fascinating, but it tells us almost nothing about what a world like Earth might be like around a star like the Sun. A planet around Alpha Centauri A would be something else entirely. It would be a world warmed by genuinely sun-like light, for the first time in the history of direct observation. It would let us ask whether the conditions that produced us are common or rare, not in the abstract, not as a statistic spread across the galaxy, but right here, at the nearest possible address. That is why this particular star has obsessed astronomers for generations. It is the closest thing we have to a mirror, and for 70 years that mirror stayed dark. You might wonder why it took so long. We have, after all, gotten very good at finding planets we cannot see directly. We watch for the tiny gravitational wobble a planet induces in its star as it tugs the star back and forth. We watch for the faint, regular dimming when a planet crosses in front of its star and blocks a sliver of its light. We even, in rare cases, photograph planets directly, catching the faint glow of young, hot worlds still warm from their own formation. We have refined these methods over decades, and they have worked spectacularly well across the galaxy. So why not here? Why not at the one address that matters most? The answer is the part that almost nobody expects. The very thing that should make Alpha Centauri easy, its closeness, is exactly what makes it nearly impossible. Proximity, which should have been our greatest advantage, turned into the cruelest obstacle. And to understand why, you have to understand that finding a planet next to a star is not like finding a star in the dark. It is like trying to find something very faint right next to something almost unbearably bright. The closer and brighter the star, the worse the problem becomes. We will get into exactly how that trap works, and how a telescope that was never designed for this job somehow sprang it open. But for now, hold on to this image, the nearest porch light in the galaxy, burning so fiercely that for 70 years it blinded every instrument we aimed at it, hiding whatever might be standing in its glow. There is a way to feel that distance rather than just read it, and it has to do with time. When you look at Alpha Centauri, you're not seeing the star as it is. You're seeing it as it was 4.5 years ago, because that is how long its light needed to reach you. If something dramatic happened there this morning, a flare, a flicker, anything, you would not learn of it until you were 4.5 years older. Every glance at that point of light is a glance into the past, a small act of time travel built into the simple business of looking up. The nearest star is always, in a sense, a memory. And if that is true of the nearest one, it is overwhelmingly more true of everything else, since most stars we study show us light that began its journey before any human civilization existed. Consider too what it means that this is a family of 3 rather than a single star, because the arrangement matters for everything that follows. Alpha Centauri A and B are bound to each other in a relatively close partnership, 2 sun-like fires circling a shared centre. Proxima, the faint red ember, is bound to both of them, but at an almost absurd remove, drifting roughly 13,000 astronomical units out, so far that a single loop around the pair takes it on the order of 500,000 years. Proxima happens to be slightly closer to us than its 2 brighter siblings at the moment, which is why it technically holds the title of nearest individual star. But it is the 2 sun-like stars that have always drawn the longing, because they are the ones that resemble home. The reason that resemblance matters so much is worth stating plainly, since it is the quiet engine under this entire story. We have exactly one example of a living world, our own, and it formed around a particular kind of star. When we ask whether we are alone, what we are really asking is whether the conditions that produced us are common or freakishly rare. A planet around a red dwarf, however interesting, cannot answer that question, because a red dwarf is a different kind of star with a different kind of light and a different kind of violence. A planet around Alpha Centauri A could begin to answer it, because that star is so nearly a copy of the Sun. For 70 years, the answer stayed locked behind the glare, and the wanting only grew, because the closer a question sits to home, the harder it is to leave alone. People have been looking at this star for as long as people have looked up. In the southern sky, two bright stars are often called the pointers, because they aim the eye toward the Southern Cross, and the brighter of the two is Alpha Centauri. Ancient navigators used it to find their way across waters they had no charts for, never knowing that the steady point guiding them was the nearest doorway out of the entire solar system. The wondering about it is not a modern thing. It is a question that has been quietly handed down, generation to generation, each one inheriting the same blank where an answer should be. What makes our moment different is not that we wonder more, but that for the first time we have built a machine capable of beginning to answer, which means the question that every prior generation had to leave open may be closed within the lifetime of people listening tonight. There is a small irony worth savouring here. The single closest star to our Sun is not one of the two bright points you can pick out on a clear southern night. It is Proxima, the faint red ember, too dim to see without a telescope. The nearest star of all is invisible to the unaided eye, hiding in plain sight beside its brighter siblings, which is a fitting overture for a system that has spent 70 years hiding its planets behind its own light. Even our closest neighbours do not give themselves up easily, and the work of seeing them clearly is exactly that. Work. The slow trading of wondering for knowing, one hard-won observation at a time. Part 2. The easiest target that wasn't. Imagine trying to photograph a single firefly hovering right beside a searchlight. The searchlight is pointed more or less at you. Its beam floods your camera, drowns your lens in glare, scatters light into every corner of the frame. Somewhere in that blaze, a tiny insect is glowing with its own soft light, but that light is thousands of times fainter than the beam beside it. You know the firefly is there. You simply cannot pull its faint spark out of the overwhelming flood. That is the problem of Alpha Centauri, and once you see it clearly, the 70-year silence stops being a mystery and starts being almost inevitable. Alpha Centauri A is the third brightest star in the entire night sky. Only Sirius and Canopus outshine it. On a clear night in the southern hemisphere, it dominates its corner of the sky with a yellow-white brilliance that ancient sailors once used to steer across oceans they had no maps for. That brightness is partly because the star is genuinely luminous, pumping out about 50% more energy than our Sun, and partly again because it is so close. A nearby fire looks brighter than a distant one, even if the distant one is larger. Alpha Centauri is a sun-like fire burning right next door, and from the point of view of a sensitive instrument trying to detect something faint beside it, that nearness is a catastrophe. Now make the problem worse, because reality did. Alpha Centauri A does not burn alone. Its companion, Alpha Centauri B, orbits close enough that during certain decades the two stars come within about 11 astronomical units of each other, roughly the distance from our Sun out to Saturn, and at their widest they separate to about 36 astronomical units. From Earth's vantage, that means a second blazing star sits right next to the first one in the field of view, throwing its own flood of contaminating light across any detector you point at the pair. It is no longer one searchlight beside your firefly. It is two, at slightly different positions, and there is no single trick that can block them both at once. Then there is the motion. Most stars appear to sit nearly still against the background of the sky over a human lifetime. Alpha Centauri does not. It has one of the largest proper motions of any star visible to the naked eye, drifting across the sky at a rate that, while it sounds tiny, is enormous by the standards of precision astronomy. The star slides measurably against the distant background from year to year. For a telescope that needs to hold a target locked in exactly the right spot for hours at a time, to a precision finer than a tiny fraction of an arcsecond, a moving target is a nightmare. Aim for where the star was, and by the time you observe, it has crept somewhere else. and because the system lies almost directly in the plane of the Milky Way, the field around it is crowded with faint background stars, thousands of them, any one of which could masquerade as a planet if you were not extraordinarily careful. A faint dot near Alpha Centauri might be a world orbiting our nearest neighbour, or it might be a distant galaxy, billions of light years away, that happens to line up behind the nearby star by pure coincidence. Sorting the one from the other is its own enormous challenge. Stack all of this together, and you begin to feel the shape of the trap. The target is too bright for sensitive instruments. It comes with a second bright star that floods the frame. It refuses to hold still, and it sits against a confusing thicket of background light. Every single advantage you would expect from a nearby star turns, on inspection, into a liability. The contrast between the star and any planet beside it is staggering. A sun-like star outshines a Saturn-sized planet by something on the order of 10,000 to 1 or more. To find that planet, you need an instrument that can detect a signal 10,000 times fainter than the blinding glare sitting right beside it, and you need to do it while the whole arrangement drifts across the sky and a second star tries to ruin everything. For decades, the conservative conclusion among many astronomers was simple. Alpha Centauri was just too hard. Better to point our best instruments at fainter, more distant, better-behaved stars, where the contrast problem was manageable and the target sat politely still. The nearest porch light in the galaxy would have to keep its secret a while longer. There was something almost poetic in the frustration. The one place we most wanted to look was the one place our methods broke down. The firefly beside the searchlight glowed on, unseen, exactly because it was so close that the searchlight beside it was overpowering. But difficulty is not the same as impossibility, and there is a particular kind of scientist who hears the word impossible as an invitation rather than a verdict. Somewhere in this story, a telescope that was built to study the faintest, most distant objects in the entire universe was about to be turned around and aimed at one of the brightest objects in our own backyard, which is roughly like using an ocean submersible to climb a mountain. Almost everyone agreed it was the wrong tool for the job. A few people thought otherwise, and the question of who was right would take more than a decade, a few spectacular failures, and a single faint dot of light to answer. Hold on to the firefly. We're going to come back to it when it finally shows itself. The contrast problem deserves a number, because the number is what makes the difficulty visceral. A sun-like star outshines a planet the size of Saturn by something on the order of 10,000 to 1, and at certain wavelengths far more than that. To pull the planet out, an instrument must detect a signal 10,000 times fainter than the blaze sitting right beside it, in the same tiny patch of sky, at almost the same moment. It is not enough to be sensitive. You have to be sensitive while staring directly into the thing that is trying to blind you. That is a fundamentally different and harder problem than simply detecting something faint in an otherwise dark sky. The proper motion adds insult to that injury. Alpha Centauri drifts across the sky fast enough that, over a human lifetime, its position shifts by an amount you could almost notice against the background of more distant stars. For naked-eye stargazing, that drift is charming and irrelevant. For a telescope that must hold its target fixed behind a mask to a precision of thousandths of an arc-second for hours at a stretch, it is a moving goalpost. Aim where the star is today, and it will have crept elsewhere by the season you actually observe. The instrument cannot simply memorize a location, because the location is alive, and then the companion makes the field itself treacherous. As Alpha Centauri A and B circle each other over their roughly 80-year period, their separation as we see it changes from decade to decade, but through these years the second star sits close enough to throw its light across any detector aimed at the first. There is no mask that blocks two bright stars at two different positions at once. Even a flawless suppression of star A would leave the glare of star B smeared across the frame. Add the crowded backdrop of the Milky Way behind the system, thick with faint stars and even fainter distant galaxies, and any single dot you find becomes a riddle in itself. Is it a planet bound to our neighbour, or a galaxy billions of light years beyond it, lined up by sheer coincidence? The firefly beside the searchlight was never going to be easy. The wonder is that anyone thought to try at all, and that the trying eventually worked. It is worth knowing that direct imaging was not the only method that broke down here. The wobble technique, which detects a planet by the tiny tug it gives its star, struggles at Alpha Centauri because the two bright stars tug on each other so strongly that a planet's far gentler pull is buried in the noise of the binary's own motion. The transit method, watching for a planet to cross its star's face and dim it slightly, only works if the orbit happens to line up edge-on with our view, and long monitoring of Alpha Centauri has turned up no such crossings, which constrains but does not rule out closer worlds. Every tool in the Planet Hunter's kit, the ones that worked so well across the rest of the galaxy, found this particular system harder than almost anywhere else. The nearest star was, by a cruel twist, among the most difficult of all, and that is the frustration that hung over the whole effort, until heat-seeking from space finally offered a way in. It helps to remember how unusual Swan would be among the planets we have actually photographed. Nearly every directly imaged world so far is a young hot giant orbiting far from its star, tens or even hundreds of astronomical units out, where the glare is easy to escape and the planet still blazes with the warmth of its own birth. S1 is the opposite on every count, old rather than young, cool rather than hot, and tucked in close to its star rather than flung far away. That is precisely why it was so hard to catch, and precisely why catching it matters. It would be the first member of a population we have never been able to see, the mature, cold, close-in worlds that resemble the planets of our own settled system. Part 3. A telescope built for the opposite job. When engineers spent more than 20 years and roughly $10 billion designing and building the James Webb Space Telescope, they had a very specific dream in mind, and that dream was almost the exact opposite of staring at a bright nearby star. They built Webb to look as far back in time and as far out into space as humanly possible. They wanted to catch the faint, stretched-out light of the very first galaxies, objects so distant that their light has been travelling for more than 13 billion years, smudges so dim that no instrument before could resolve them. Every part of the telescope was optimised for faintness and distance. Its enormous golden mirror, its position 1,000,000 miles from Earth at a gravitational balance point called Lagrange Point 2, its detectors tuned to catch ancient photons that crossed almost the entire history of the universe to reach it. Webb was a machine for seeing the dimmest things that exist, so pointing that machine at Alpha Centauri A, one of the brightest stars in our sky, seemed to many people like a category error. It seemed almost dangerous. These detectors were precious, designed to register the faintest whispers of light, and here was a proposal to flood them with a roaring nearby fire. There were real fears about overwhelming the instruments, about pointing this delicate, irreplaceable observatory at exactly the kind of blazing target its standard operating rules were written to avoid. The cautious instinct, the responsible instinct even, was to keep Webb on its intended mission, gazing at the distant young universe, and leave the bright, difficult neighbours to someone else. One astronomer refused to accept that. Charles Beichmann, a veteran researcher connected to NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute, had been thinking about planets around Alpha Centauri since before Webb even launched. He understood every objection. He also understood something the objections were missing, which was that Webb had a particular ability that no other instrument possessed, an ability that might just turn the impossible target into a possible one. His idea was not to look for a planet's reflected light, the faint mirror glint of starlight bouncing off a world. His idea was to look for the planet's own heat. To see why that matters, you have to think about how planets shine. A young planet, freshly formed, still glows with the leftover heat of its own creation, radiating brightly in the near-infrared, the kind of light just beyond what our eyes can see. That is why almost every planet ever directly photographed has been young and hot, a world still cooling from its violent birth. But Alpha Centauri A is about 5 billion years old, roughly the same age as our Sun. Any planet around it would have formed billions of years ago and long since lost that birth heat. It would be cool, mature, settled. It would not blaze in the near-infrared like a newborn world. Instead, whatever warmth it had would come from absorbing its star's light and re-radiating that energy as a faint thermal glow, peaking at longer wavelengths in the mid-infrared. And the mid-infrared is precisely where one of Webb's instruments achieves its sharpest sensitivity. That instrument is called MIRI, the mid-infrared instrument, and Bateman's plan centered on a particular filter within it, tuned to a wavelength of 15.5 micrometers. A planet orbiting in the temperate zone of Alpha Centauri A would have a temperature somewhere in the range of a couple hundred Kelvin, cold by human standards, far below the freezing point of water, but warm enough to emit a faint signature at exactly the mid-infrared wavelengths where MIRI was most able to catch it. The physics genuinely favoured this approach for a mature system. You were not trying to see the planet's reflected light at all. You were trying to feel its heat across 4.5 light years. But detecting that faint warmth meant solving the contrast problem we have been circling, the Searchlight and Firefly disaster, and MIRI had a tool for that too. It carried a coronagraph, an instrument designed specifically to blot out the overwhelming light of a star so that fainter objects beside it could be seen. A coronagraph works by placing a carefully shaped mask over the position of the star on the detector, creating in effect an artificial eclipse. The simplest way to picture it is a tiny, precisely engineered version of holding your thumb up to block the sun so you can see something near it. The particular mask in MIRI, called a 4-quadrant phase mask, did its work not by crudely covering the star but through a subtle trick of physics, using the wave nature of light itself to make the starlight cancel out, interfere with itself destructively, and collapse to a fraction of its former brightness, while light from objects sitting just slightly off-center pass through relatively untouched. When a coronagraph works well, the effect is something close to magic. The star's blinding light is suppressed by factors of hundreds or thousands, and a faint companion that was utterly drowned moments before suddenly has a chance to emerge. For most of the stars Webb observed, the coronagraph performed beautifully, because most stars were at comfortable distances and comfortable brightnesses, well within the rules the instrument was designed around. The trouble, of course, was that Alpha Centauri broke every one of those rules at once. It was too bright, it moved too fast, it carried a second bright star right beside it, and it sat in a crowded field. So the plan was audacious, and it asked the telescope to do something its designers had never quite intended. It asked Webb, the great machine for seeing the faint and the distant, to turn around and detect the heat of a cool, mature planet hiding in the glare of one of the brightest, fastest-moving, most badly behaved stars in the whole sky. On paper, the physics gave it a chance. In practice, nobody knew whether it could actually be done, and the first people to try would have to invent entirely new ways of operating the most expensive telescope ever built. The skeptics had decades of reasonable caution on their side. Bateman had a stubborn idea about heat instead of light, and a small team willing to find out whether the impossible target might, just barely, be possible after all. It helps to understand why a telescope built for distance is so reluctant to look close. Webb spent its long development being optimized for one overriding goal: to gather the faint stretched light of the early universe, the dim smudges of galaxies whose light has travelled for more than 13 billion years. Everything about it serves that aim, from the enormous segmented mirror to its frigid operating temperature to its perch at Lagrange Point 2, a gravitational balance point about 1 million miles from Earth, where it can stare into the dark without our planet getting in the way. A machine tuned that finally for faintness flinches, understandably, at the idea of being pointed at one of the brightest stars in the sky. The genius of the plan was to use the telescope's strength rather than fight its caution, and the strength was the mid-infrared. Light comes in a spectrum, and where a thing shines tells you what kind of thing it is. Young planets, still glowing with the leftover heat of their formation, blaze in the near-infrared, the band just past visible red, which is why nearly every planet ever directly photographed has been a hot adolescent world. But Alpha Centauri A is about 5 billion years old, and any planet around it would be just as ancient, long since cooled. Such a world would not blaze. It would smoulder faintly in the longer wavelengths of the mid-infrared, throwing off the heat it absorbs from its star rather than the heat of its birth. That mid-infrared band, useless for many purposes, is exactly where one of Webb's instruments does its finest work. The coronagraph that would block the star is itself a small marvel worth dwelling on. Rather than simply pasting an opaque dot over the star, the 4-quadrant phase mask manipulates the wave nature of light, shifting parts of the incoming starlight so that they interfere with and cancel one another, collapsing the star's brightness by factors of hundreds or thousands, while leaving light from just off-center largely intact. It is, in effect, using light against itself, persuading the star's own glare to erase a portion of itself through destructive interference. When it works, a companion that was utterly drowned can suddenly stand clear. The catch, always, was that this elegant trick had been designed for well-behaved stars at comfortable distances, and Alpha Centauri was neither. The plan asked the most distance-loving telescope ever built to feel the faint warmth of an old, cool world hiding beside a roaring nearby fire. On paper, the physics allowed it. Whether the machine could actually do it was a question only the attempt could answer. The caution around pointing Webb at a bright star was not timidity. It was stewardship. The telescope cost roughly $10 billion and took more than 2 decades to design, build, test, and fly, and its detectors were irreplaceable, tuned to register the faintest whispers from the early universe. Nobody wanted to be the person who aimed that priceless instrument at a roaring nearby fire and damaged it. The conservative path, study the distant universe the telescope was built for and leave the bright, difficult neighbours alone, was the responsible default for good reason. Turning the machine toward Alpha Centauri really was something like using an ocean submersible to climb a mountain, or a surgical blade to fell a great tree, the wrong tool by every obvious measure. It took a particular stubbornness to look at all that reasonable caution, and decide that the prize on the other side was worth the risk of trying anyway. The choice of the 15.5 micrometer filter was not arbitrary. An object near 225 Kelvin radiates most of its heat in the mid-infrared, and that particular wavelength is where MIRI reaches its finest sensitivity, the sweet spot where a cool, mature planet glows most clearly against the dark. Picking the right wavelength was as important as building the right mask, because even a perfect coronagraph is useless if you're listening for the planet at a colour it barely shines in. The team was, in effect, tuning the instrument to the exact frequency of a cold world's whisper. Part 4. Tricking the telescope. The first problem the team had to solve was almost embarrassingly basic, and it nearly stopped the whole effort before it began. Webb could not look directly at Alpha Centauri A. The star was simply too bright for the telescope's normal way of locking onto a target. When Webb wants to observe something, it first acquires the target, finding it, centering it, fixing its gaze using fine guidance sensors that were never built to stare into a fire this intense. Pointing those sensors straight at one of the brightest stars in the sky risked overwhelming them entirely. The standard brightness limits existed for a reason, and Alpha Centauri A sailed far past them. The telescope, in a sense, could not safely open its eyes on the very thing it was being asked to study. The solution the team invented was as clever as it was nerve-wracking, and it had a name that captures the whole gamble: blind offsetting. Instead of looking at Alpha Centauri A directly, the telescope would first lock onto a different, more manageable star nearby, a calm reference point it could safely acquire. Then, without ever pointing straight at its real target, it would shift its gaze by a precisely calculated amount, a blind hop across the sky, landing Alpha Centauri A exactly behind the coronagraph's mask. It is the equivalent of refusing to stare into a spotlight by first fixing your eyes on a dim lamp off to the side, then turning your head by an exact memorized angle so that the spotlight lands precisely behind your raised thumb, all without ever looking at it. If your angle is even slightly off, the spotlight blazes around your thumb and ruins everything. For the dim lamp, the reference star, the team chose a red giant called Epsilon Muscae, sitting about 330 light-years away in the southern constellation Musca. It was bright enough to acquire easily, faint enough to be safe, and positioned in a way that made the geometry work. Webb's guidance systems could lock onto Epsilon Muscae without any trouble. Using completely ordinary procedures, from that safe perch, the telescope would then perform its blind leap to Alpha Centauri A. But here the moving target came back to haunt them. Remember that Alpha Centauri does not hold still. It has one of the largest proper motions of any naked-eye star, drifting measurably across the sky. On top of that, because it is so close, it shows a large parallax, an apparent back-and-forth shift caused by Earth's own motion around the Sun. Over the course of a year, the star's apparent position swings by about 750 milliseconds, a wobble caused entirely by our changing vantage point. This meant that the exact angle of the blind leap was never the same twice. Coordinates that were correct in January would place the star in the wrong spot by March. Every single observation required fresh calculations, accounting for the precise date and time, the star's drift, and Earth's position in its orbit, all computed to an accuracy measured in thousandths of an arcsecond. The team built software pipelines that recomputed the offset for each attempt, because nothing about this target could be treated as fixed. The needle they were threading kept moving, and they had to recalculate the thread every time. In 2023 they tried, and they failed. Completely. The first attempts produced data that was simply unusable. The telescope struggled to hold its precise pointing while compensating for the star's motion and its extreme brightness at the same time. The chronograph's performance dropped below the level needed to detect anything. Contamination from the bright companion star scattered everywhere across the frame. There was no planet in the results, but more discouragingly, there was no clean data at all, just a mess that confirmed everything the skeptics had been saying for years. Alpha Centauri was too hard. The telescope should go back to studying the distant universe it was built for. The cautious people had warned about exactly this, and the failure seemed to prove them right. It would have been an easy place to quit. The difficulty was real, the failure was total, and the conventional wisdom had a fresh piece of evidence on its side. But the team did not walk away. Instead, they did the unglamorous essential work that real science is mostly made of. They went back through everything that had gone wrong, failure mode by failure mode, and they redesigned their approach to address each one. They modified the pointing procedures to achieve better centering. They developed new ways of processing the data specifically built to handle the contamination pouring in from the second star. They ran exhaustive simulations, testing their methods against artificial data before risking another precious observation. They were not hoping the next attempt would work. They were engineering it to work. By the middle of 2024, the refined approach was ready, and test observations showed that the modifications had done their job. Webb could finally observe this impossible target with a sensitivity approaching the theoretical limits of what the instrument could do. The team requested and received approval for a full observation campaign, a real attempt with the rebuilt method, and so, in August of 2024, the most expensive telescope ever built, perched 1 million miles from Earth, locked onto a dim red giant, performed a blind leap across the sky calculated to the thousandth of an arcsecond, and dropped one of the brightest, fastest, most stubborn stars in the heavens precisely behind a mask the width of a whisper. Then it opened its eye and began, for hours at a time, to collect whatever faint warmth might be leaking out from beside that hidden fire. After 70 years of wanting and more than a decade of one team's particular obsession, The Firefly was about to get its photograph taken. Whether anything would be in the frame, nobody yet knew. The blind offset deserves a closer look because it is the kind of solution that sounds reckless until you realise it was the only way through. Webb could not safely lock its guidance sensors onto Alpha Centauri A because the star was simply too bright for the delicate business of target acquisition. So the team taught the telescope to look away from its own target. It would first fix its gaze on a calmer, dimmer star it could acquire without risk, and only then shift by a precisely computed angle, dropping the real target behind the coronagraph's mask without ever pointing straight at it. The whole manoeuvre depended on knowing the exact positions of both stars to thousandths of an arc-second, because an error that's small would let the star's light spill around the mask and ruin the entire observation. The reference star they chose, a red giant called Epsilon Muscae, about 330 light-years away, was bright enough to acquire easily and steady enough to trust. But the calculation behind each leap was never the same twice, and that is the part that reveals how unforgiving this target is. Because Alpha Centauri lies so close, Earth's own yearly motion around the Sun makes the star appear to swing back and forth by about 750 milliseconds over the course of a year, a parallax wobble caused entirely by our shifting vantage point. Layer the star's genuine drift on top of that, and the exact angle of the blind leap changed from month to month. Coordinates correct in one season would miss by the next. Every attempt demanded a fresh calculation tied to the precise date and time, and the team built software to recompute the offset for each observation, because nothing about this target could be treated as a constant. The 2023 failure, painful as it was, turned out to be the thing that made success possible, because it gave them concrete problems to solve rather than vague fears to manage. They went back through every way the attempt had gone wrong and addressed each one in turn, tightening the pointing, rewriting the data handling to cope with the second star's contamination, and testing the whole chain against simulated data before risking another night of precious telescope time. By the middle of 2024, they were not hoping the method would work. They had engineered it to work, and the test observations proved it. The needle was still moving, the glare was still blinding, the second star was still flooding the frame, and yet, for the first time, the team had a way to thread all of it at once. Behind the blind leap lay months of unglamorous labour at the Space Telescope Science Institute, where the operations team had to invent observing sequences that had never been attempted with this telescope. Standard procedures, refined across hundreds of successful campaigns, simply did not apply to a target this bright, this fast, and this crowded. Every part of the observation had to be built from scratch, simulated, stress-tested, and rebuilt, with no guarantee that any of it would work. The people doing this were not chasing glory in the moment. They were solving a long chain of small, exacting problems, each of which had to be right, or the whole night would be wasted. It is a side of discovery that rarely makes the story, the patient engineering that has to happen before there is anything dramatic to point at. And in this case, it was the difference between another failure and the first real look beside our nearest neighbour. This is also why the campaign needed special handling rather than an ordinary slot in the queue. After the encouraging detection, the follow-up observations were granted as urgent time, the kind reserved for targets too important to wait for the normal cycle, because a candidate planet beside the nearest sun-like star is not something you schedule casually. The whole effort lived slightly outside the telescope's routine, demanding custom sequences, fresh calculations, and rapid response. A reminder that the most interesting science often pushes against the edges of how an instrument is normally run. Part 5. The Dot in the Glare. When the data from August 2024 first came streaming back from Lagrange Point 2, crossing the 1,000,000 miles to Earth in a handful of seconds, it did not look like a triumph. It did not look like anything at all. The raw images were a chaotic ruin of light, exactly what you would expect from such a brutal observation. Alpha Centauri b blazed near the top of each frame, its scattered light throwing bright streaks and halos clear across the field. The coronagraph, doing its strange work on Alpha Centauri A, left behind complex ripple patterns where starlight had bent around the edges of the mask. Detector artifacts and diffraction spikes covered everything. To a human eye, there was no astronomy in those frames. There was only noise and abstract mess with no obvious meaning anywhere in it. If a planet was hiding in there, it was buried under layers of contamination thousands of times brighter than itself. This is the part of the story that almost never gets told, because it is not dramatic in the way a discovery is supposed to be. The planet did not appear in a flash on a screen while scientists cheered. It had to be excavated, dug out of the noise by mathematics, layer by patient layer. The team used a technique with a plain name and a clever idea behind it: reference star differential imaging. They had observed other stars using the exact same coronagraph settings, stars with no planets around them, to build a template of how the instrument behaves when nothing interesting is there. That template captured all the predictable garbage, the diffraction patterns and optical quirks that the instrument produces no matter what. By subtracting that template from the Alpha Centauri data, they could strip away the systematic mess and leave behind only what was genuinely different about this particular target. Then came another mathematical layer, methods called principal component analysis, ways of identifying and removing the correlated patterns of noise that even reference subtraction could not catch. Picture cleaning a window that is not just dirty but covered in a complicated repeating pattern of grime. First you wipe away the part of the pattern you already know is there, then you study what remains, find the next repeating structure in it, and remove that too, and again, peeling the contamination back one correlated layer at a time. Component by component, the noise thinned, and whatever lay beneath it slowly rose toward visibility. And then, after all of that processing, something stayed behind that should not have been there if the field were truly empty. At a separation of about 1.5 arcseconds from Alpha Centauri A, a single faint point of light sat in the cleaned-up images. It shone more than 10,000 times fainter than its host star. Its position placed it at roughly 2 astronomical units from Alpha Centauri A, about the distance from our Sun out toward Mars. The team gave it a name as plain as a file label, S1. After 70 years of an empty porch, there was a dot beside the light. You have to understand what 1.5 arcseconds and 10,000 to 1 actually mean to feel the weight of this. Picture standing in one city and trying to photograph a candle flame held right next to a lighthouse beam, with the candle and the lighthouse together as seen by someone on the far side of the country. The brightness gap between the flame and the beam, the impossible nearness of the two, the sheer faintness of what you're trying to catch against the blaze beside it. That is something close to what this single dot represented. It was the smallest separation between a planet candidate and its star ever achieved in direct imaging. Every other directly photographed world had been caught much farther from its star, where the glare was easier to escape. S1 sat almost on top of the searchlight, and they had pulled it out anyway. Picture the moment in the room as the final processing runs. The screen has shown nothing but noise for hours of work. Someone applies the last subtraction, the last component removed, and refreshes the image. For a heartbeat, it is the same grey static it has always been. And then, at one specific spot off to the side of the masked star, a point of light holds steady where everything around it is random. It does not flicker away on the next pass. It does not move when it should not. It simply sits there, faint and stubborn and real, exactly where a planet circling our nearest sun-like neighbour might be. Whoever is watching that screen leans in. The static is just static. But that one dot is not. After all the failures, after the decade of arguing that it could not be done, there is a firefly in the frame beside the searchlight, and someone is finally looking at its photograph. The team did not let themselves celebrate on the strength of a single point of light, and they were right not to. They first asked how likely it was that this dot was simply a fluke of noise, a random fluctuation that happened to look like a source. The answer was a measurement of statistical significance, and it came back at 5.5 sigma. In plain terms, that means the probability of random noise conjuring a signal this strong is less than 1 in 10 million. Detectors do produce spurious blips. The way flipping a coin enough times eventually gives you a long run of heads, but a 1 in 10 million run is not something you stumble into by accident. To make sure, they split the August data into independent halves and analysed each separately. Both halves showed S1, at the same place, at the same brightness. Genuine noise does not behave that consistently. Something real had been detected beside the nearest twin of our sun. Stop and sit with what that meant. Because the meaning is bigger than the data. For the entire span of human history, every person who ever wondered whether the nearest sun-like star had planets had to wonder in the dark. Every astronomer who ever pointed an instrument at that yellow-white point and came away empty-handed had to leave the question open. And now, after 70 years of wanting and $10 billion, and a telescope aimed at exactly the kind of target it was told to avoid, a single dot of light had appeared where all of them had hoped one might be. The weight of the moment was never really in the numbers. It was in the fact that the longest-running question about our closest neighbour had, for the first time, an answer that might be yes. The wondering of every prior generation had just received its first real reply. And then, of course, the universe complicated everything. The excavation of S1 from the noise is the part of the story that rewards patience, because nothing about it was instant. The raw frames that came back in August 2024 were, to any honest eye, a disaster. Full of streaks from the second star, ripple patterns where light had bent around the mask, and the ordinary speckle of detector artifacts. A planet, if it was there, was buried under contamination thousands of times brighter than itself. Pulling it out was not a matter of looking harder. It was a matter of subtracting, carefully and repeatedly, everything that was not the planet. They began with reference star differential imaging, using observations of planetless stars taken with identical settings to build a template of how the instrument misbehaves when nothing interesting is present. Subtracting that template stripped away the predictable garbage, the optical quirks the instrument produces no matter what it looks at. Then came principal component analysis, a way of finding and removing the remaining correlated patterns of noise that the first subtraction could not catch. Picture cleaning a pane of glass covered not just in dirt but in a repeating structured grime, wiping away one known pattern, then studying what is left, finding the next pattern, and removing that too, again and again, until only the genuine view remains. Layer by mathematical layer, the contamination thinned. What survived all that subtraction was a single point of light at about 1.5 arc seconds from the star, more than 10,000 times fainter than its host, sitting where a planet near 2 astronomical units would sit. To feel the difficulty, imagine photographing a candle flame held right beside a lighthouse beam, the pair seen from across an entire country. That separation, that contrast, that faintness, all of it represented the smallest gap between a planet candidate and its star ever achieved in direct imaging, the closest anyone had ever pulled a world out from beside its own glare. And the proof that it was not a phantom came from the numbers. At 5.5 sigma, the odds of random noise faking a signal this strong fall below 1 in 10 million, and when the team split the August data into independent halves, both halves showed the same dot in the same place at the same brightness. Noise does not keep its story straight like that. Something real was sitting beside the nearest twin of our sun, and for the first time, the longest-running question about that star had an answer that might be yes. Before the team would trust the dot, they tried hard to prove it false, which is exactly how it should be. They ran what are called injection recovery tests, deliberately inserting fake planet signals into the raw data to confirm that their processing could tell a genuine source from an artifact, and one behaved like the real ones, not the fakes. They checked whether it might be a distant background galaxy lined up by chance, and found no catalogued object at its position. They checked whether it might be a drifting foreground body, and found that it stayed put relative to the star across the observation, as a bound companion should. Every test designed to expose a false positive came back clean. Only after the dot had survived that gauntlet did the team allow themselves to call it a candidate, sitting about 2 astronomical units from the star, out near where Mars would orbit in our own system, more than 10,000 times fainter than the fire beside it. 2 astronomical units is a homely sort of distance, which is part of what makes S1 so compelling. It is roughly where Mars would sit in our own system, well inside the kind of orbit we think about when we think about worlds near a sun-like star, not lost in some frozen far suburb. The candidate separation on the sky, about 1.5 arcseconds, sounds vanishingly small, and it is, but it represents the closest any planet candidate has ever been pulled out from beside its star in direct imaging. Closeness, the thing that made the whole search so hard, also makes the prize uniquely valuable. Part 6. The Planet That Vanished. The team knew that one observation, however strong, could not prove a planet. A real planet does not simply sit still for a single photograph and call it done. It orbits. It moves along a path dictated by gravity, shifting its position over time according to laws we have understood since Kepler and Newton. To confirm that S1 was a genuine world, rather than some exotic trick of the instrument or a one-time coincidence, they needed to see it again, at a different time, in a different place, moving the way a bound planet must move. So the Space Telescope Science Institute granted urgent follow-up time, the kind reserved for targets too important to wait for the normal scheduling cycle. 2 more observations were arranged for February and April of 2025, using the exact same hard-won techniques that had revealed S1 in the first place. If S1 was real, it should appear again, perhaps shifted a little along its orbit, and that shift would begin to reveal the shape and size of its path. The February observation went perfectly, from a technical standpoint. Every system performed as designed. The blind offset placed Alpha Centauri A precisely behind the mask. The detectors collected light for hours while the telescope held rock steady. The data came home clean. The analysis pipeline activated, the same one that had excavated S1 from the August noise, running through reference subtraction and principal component analysis with mechanical precision. Layer after layer of contamination peeled away, just as before, revealing whatever astronomical signal lay beneath the glare. The scientists watched the field clear, searching the region where S1 should now appear. Nothing was there. The spot where S1 had blazed with 5.5 sigma significance just months earlier showed only empty space. No strong detection rose out of the noise. No marginal hint of a planet flickered at the edge of the data. There was nothing but random fluctuation where a Saturn-sized world should have been plainly visible. The team did what any careful scientist does when the universe refuses to cooperate. They assumed they had made a mistake. They reran the pipeline with different settings. They tried alternative algorithms. They went back to the raw data and examined it directly, looking for any trace of a signal that the processing might have accidentally scrubbed away. Every approach gave the same answer. The February data contained no detectable planet anywhere in the coronagraph's sensitive field. S1 was gone. April offered one more chance. Perhaps February had simply been an unlucky epoch, some transient condition that had spoiled the sensitivity. Perhaps 2 more months of orbital motion would carry the planet back into a position where it could be seen. The April data arrived and went through the same careful scrutiny. The pipeline churning, the scientists searching every corner of the cleaned-up field with a kind of stubborn thoroughness that was starting to feel like desperation. More empty space, more null results. The candidate that had electrified the team in August, the dot that might have been the most significant exoplanet detection in history, had completely disappeared. Whatever Webb had caught in 2024 no longer showed itself to the most powerful space telescope ever built. Picture the second control room months after the first. The screen runs through the same processing that once delivered a miracle. The static thins, the layers peel back, and the spot everyone is staring at, the spot that should hold a planet, clears to nothing. Someone reruns it with new parameters. Nothing. Someone pulls up the raw frames and goes through them by hand. Nothing. The room is not loud. There is no drama, just the quiet, deflating sound of a result that refuses to be what you wanted it to be. A doctoral student at the California Institute of Technology, Aniket Sanghi, a co-author on the discovery, captured the whole strange situation in a single phrase that would come to define it. They were dealing, Sankey said, with the case of a disappearing planet. The object that had carried so much hope seemed to have evaporated into the dark between observations. This is the moment the story could have ended, and ended badly. A single detection, however strong, followed by 2 clean non-detections, is exactly the pattern you would expect if the original signal had been a fluke after all. The skeptics had a new and powerful argument. Maybe S1 had never been real. Maybe August 2024 had been that 1 in 10 million accident, an improbable noise spike that survived every test by sheer bad luck, fooling careful people into believing they had found a world. Extraordinary claims demand extraordinary evidence, and a planet that shows up once and then refuses to appear twice is not obviously extraordinary evidence. It might just be a ghost. But the team did not accept that conclusion, and not out of stubbornness. They accepted a harder, more interesting fact about the universe, which is that a planet vanishing from view does not mean a planet ceasing to exist. Planets do not blink out of reality. If S1 was real, it was still out there, still bound to Alpha Centauri A by gravity, still moving along whatever path it had always followed. The question was not whether a real planet could disappear. The question was whether a real planet, moving as real planets must, could move in a way that took it out of sight of even this telescope for exactly these months, and then potentially bring it back. That question turned the entire mystery inside out. Because the answer, when they worked it through, was not only yes. The answer was that for more than half of all the orbits S1 could plausibly be on, disappearing was exactly what it was supposed to do. The non-detections, which looked at first like a refutation, were about to become something much stranger. They were about to become evidence. The decision to chase confirmation rather than celebrate was the correct one, and the reasoning behind it is the reasoning that protects science from fooling itself. A single detection, no matter how strong, cannot prove a planet, because a planet is defined by its motion. A real world orbits, shifting its position over time along a path that gravity dictates, and the only way to be sure S1 was a world rather than a one-time trick was to catch it again, somewhere new, moving the way a bound planet must. So the team secured urgent follow-up time and aimed Webb back at Alpha Centauri A in February, and again in April of 2025, using the same hard-won method that had revealed S1 in the first place. The cruelty of what happened next was that nothing went wrong, technically. The February observation was flawless. The blind offset landed cleanly, the telescope held steady, the data came home pristine, and the pipeline ran exactly as it had before, peeling back the contamination layer by layer toward the spot where S1 should now sit. And the spot was empty. No strong signal rose from the noise, no faint hint lingered at the edge of detection, nothing but random fluctuation where a Saturn-sized world should have been obvious. The team assumed error, as careful people do, and reran everything, trying new settings, alternative algorithms, even going back to the raw frames by hand to make sure no real signal had been scrubbed away by accident. Every path led to the same empty answer. April was the second chance, and it failed the same way. 2 more months of orbital motion might have carried the planet somewhere visible, and the team searched the new data with a thoroughness that edged toward desperation, and still found nothing. The dot that had carried so much hope had simply ceased to appear. One of the discovery's authors, a doctoral student named Aniket Sanghi, summed up the whole unsettling situation in a phrase that stuck, calling it the case of a disappearing planet. It was the moment the story could have collapsed, because a single detection followed by 2 clean misses is exactly the pattern you would expect from a fluke. The skeptics had their argument ready, but the team held on to a harder fact, the fact that planets do not stop existing simply because we stop seeing them. If S1 was real, It was still out there, still bound, still moving. The question was no longer whether it had vanished. The question was whether a real planet, obeying gravity, could move in a way that hid it for exactly these months. And that question was about to rewrite the entire meaning of the empty frames. The hardest part of the disappearance was not technical but psychological, because hope is heavy to set down. The team had pulled off something many thought impossible, had seen a real dot beside the nearest twin of the sun, and then watched the universe refuse to show it again, twice. The skeptic's case was not foolish. A signal that appears once and then misses twice is the textbook shape of a fluke, and honest scientists had to hold that possibility open. But holding it open is not the same as accepting it, and the team kept returning to a single stubborn truth, that the strength and consistency of the August signal made the fluke explanation strain against its own numbers, while the alternative, a real planet simply moving out of view, required nothing strange at all. The question was no longer whether the planet had vanished. It was whether vanishing was something a real planet would naturally do. The temptation to quit after 2 empty observations must have been real, and the team's refusal to do so is the quiet centre of this story. They did not insist the planet was there out of pride. They simply followed the logic where it led, which was toward a universe in which a real planet can drop out of view without ceasing to exist. Choosing to keep asking rather than declaring the candidate dead is what kept the door open long enough for the orbital modelling to reveal what the empty frames actually meant. Part 7. How absence becomes evidence. To understand how a missing planet can be evidence for a real one, you have to abandon a comfortable assumption, which is that a good telescope sees equally well in every direction around a star. A coronagraph does not work that way. Its ability to detect a faint companion changes dramatically, depending on exactly where that companion sits relative to the masked star, and the reasons come down to the stubborn physics of light itself. Once you understand those reasons, the disappearance of S1 stops looking like a contradiction and starts looking like a prediction coming true. Start with the mask. The coronagraph blocks the star by covering its central image, creating that artificial eclipse we talked about. But no physical mask can ever block light perfectly, because light is a wave, and waves bend around edges. The phenomenon is called diffraction, and it is the same reason you hear someone talking around a corner even when you cannot see them. When starlight hits the boundaries of the coronagraph's mask, some fraction of it bends around those edges instead of being cleanly blocked, and that bent light spills outward into complex patterns of residual brightness. Close to the star, this leaked, diffracted light is intense, and it drowns any faint planet trying to emerge there. Far from the star, the planet's own signal becomes too weak to stand out against the detector's noise. Only in a particular ring of separations, a kind of sweet spot, does the contrast become good enough to detect a world at all. Too close, and the leftover starlight wins. Too far, and the planet fades into nothing. The detectable zone is narrower than many people first assumed. It gets more complicated because the sensitivity also changes with direction. The 4-quadrant phase mask, by its very design, suppresses starlight differently along different angles around the star, depending on how the geometry of the mask lines up with the structure of the telescope. Some directions achieve excellent contrast, other directions stay hopelessly contaminated. This means a planet can be perfectly detectable when it sits along one direction from its star and then become completely invisible when its orbit carries it to an unfavourable angle, even if its distance from the star has barely changed. The instrument has blind spots, not because it is broken, but because that is how the physics of masking and diffraction conspire to work. Now bring the orbit into it. If S1 travels on a circular path, it stays at roughly the same distance from its star at all times. But if it travels on an eccentric path, an elongated ellipse rather than a near-perfect circle, then its distance from Alpha Centauri A changes continuously as it goes around. Sometimes it swings in close to the star, into the region where diffracted glare overwhelms everything, and detection becomes impossible. Sometimes it retreats outward, into the sweet spot where the coronagraph can actually catch it. A planet on an eccentric orbit would naturally spend part of its year visible and part of its year hidden, not because it goes anywhere unusual, but because the telescope's ability to see it rises and falls along its path. And if the orbital geometry is unlucky, the planet might even pass nearly in front of or behind the star from our point of view, vanishing through simple alignment. So the February and April non-detections did not have to mean that S1 was never there. They could mean exactly the opposite. They could mean that S1 was real, and that between August and the following spring it had moved along its orbit into one of those blind regions, too close to the star or at an unfavourable angle, where even Webb at its best simply cannot see. The planet would not have vanished. It would have done nothing more dramatic than continue orbiting, sliding from a place where we could see it to a place where we could not. This was a beautiful idea, but the team did not want a beautiful idea. They wanted a number. So they tested the hypothesis with brute computational force. They generated millions of simulated orbits, every possible path S1 could be on, that was consistent with the observations, varying the period, the eccentricity, the tilt, the orientation. Each simulated orbit had to obey the real constraints of the system, including the requirement that it stay gravitationally stable in the presence of the second star, Alpha Centauri b, over long stretches of time. Then, for each of those allowed orbits, they asked a simple question. If the planet were really on this path, would it have been visible in August 2024, and would it have been hidden in February and April 2025? The result is the number that turned the whole story around. They found that 52% of the gravitationally stable orbits fitting the data would naturally produce non-detections in both February and April. More than half of all the paths S1 could plausibly be on carried it, during exactly those months, into regions where Webb's coronagraph drops below the sensitivity needed to see it. Read that again, because it is the hinge of everything. The disappearance was not improbable. It was the single most likely outcome. A genuine planet on a typical allowed orbit was more likely to be invisible during those follow-up windows than to be visible. The absence of a detection provided essentially no evidence against the planet's existence, because absence was precisely what a real planet would most often deliver. There is something quietly profound in that, and it is worth letting it land. We are used to thinking of seeing as believing, of presence as proof and absence as disproof. But here was a case where a thing could be entirely real, and for long stretches, entirely unobservable, and where the failure to see it was not a strike against its reality, but a consequence of how reality and observation interact. The planet, if it existed, was out there the whole time, moving exactly as gravity demanded, indifferent to whether our instruments happened to be able to catch it in any given month. In a sense, the universe already knew the answer to whether S1 was real. It had always known. The not knowing was entirely on our side, a limitation of geometry and glare, not a fact about the planet. That phrase is worth holding on to because it will come back. The universe already knows the answer. Out there, 4.5 light years away, the truth about S1 is settled, fixed, complete. Either a Saturn-sized world is tracing its long ellipse around Alpha Centauri A right now, or it is not, and nothing we do changes which of those is true. All our telescopes can do is wait for the geometry to turn favourable again, for the planet, if it is there, to swing back out into the light where we can finally catch it a second time. The non-detections did not close the case. They reopened it on far more interesting terms, and the next clue, it turned out, had been sitting in an old data set for 6 years, dismissed and nearly forgotten, waiting for someone to realise what it might have been. It is worth slowing down on why a coronagraph has blind spots at all, because the answer is built into the nature of light. The mask that blocks the star cannot block it perfectly, because light bends around edges through diffraction, the same effect that lets sound travel around a corner. Some starlight always leaks around the mask and spills outward, and close to the star that leaks light is so intense that it buries anything faint trying to appear there. Astronomers call the boundary of the usable region the inner working angle, the closest a planet can sit to its star and still be pulled out of the leftover glare. Inside that boundary, even a bright planet drowns. The detectable region is a ring, not a circle, and the ring is narrower than people first hoped. Layer on top of that a second effect, which is that the four-quadrant mask does not suppress the star equally in every direction. Along some angles it achieves beautiful contrast, and along others it stays stubbornly contaminated. So a planet's visibility depends not only on how far it sits from its star, but on which direction it lies, and both of those things change as the planet moves along its orbit. A world can be plainly visible at one point in its year and completely lost a few months later, having done nothing more exotic than continue circling. The instrument is not failing. It is simply blind in particular places by the unavoidable physics of masking light with light. This is what makes an eccentric orbit so important to the story. A planet on a stretched elliptical path swings nearer and farther from its star across each loop, dipping into the blinding inner region near its closest approach and rising back into the detectable ring as it retreats. Such a world would naturally spend part of its orbit seen and part of it hidden. And when the team simulated millions of allowed orbits for S1, demanding that each one fit the data and stay gravitationally stable, they found that 52% of those orbits would produce non-detections in exactly February and April of 2025. More than half. The disappearance was not improbable. It was the single most likely outcome for a real planet. There is a quiet lesson buried in that number, one that runs against a powerful instinct. We treat seeing as believing and absence as disproof, but here was a case where a thing could be entirely real and, for long stretches, entirely unseeable, where the failure to find it was not evidence against it, but a predictable consequence of geometry and glare. Out there, the truth about S1 was already settled. The not knowing was entirely on our side, and the universe, indifferent to our instruments, already knew the answer. What the 52% figure really buys is a reframing of what science is doing here. The non-detections do not confirm the planet, and they do not refute it. What they do is constrain its orbit, narrowing the family of possible paths, ruling out the ones that would have kept S1 visible, and favouring the ones that would have hidden it. This is how the field actually advances, not in single triumphant verdicts, but in a slow tightening of possibility, each observation shaving away configurations that no longer fit. It is less satisfying than a clean yes or no, but it is far more honest, and it is also more powerful, because a constraint that survives many tests becomes very hard to escape. The answer about S1 is not being declared. It is being cornered, observation by observation, until there will be nowhere left for an unreal planet to hide and no reason left to doubt a real one. Seeing is not always believing, and Alpha Centauri makes that lesson concrete. Whether we can detect S1 in a given month depends not on whether it exists, but on where it happens to be along its orbit and how the instrument's blind zones fall. The planet's reality and our ability to observe it are two separate things, and confusing them is exactly the trap the team had to avoid. The answer out there is fixed. Our access to it comes and goes with the geometry, which means the search is in part simply a matter of waiting for the right moment to look. Part 8. The Ghost. From 2019. Long before Webb ever turned its golden mirror toward Alpha Centauri, another telescope had caught a whisper there and not known what to make of it. In 2019, astronomers using the European Southern Observatory's Very Large Telescope in the mountains of Chile had run a specialized campaign to search for planets around Alpha Centauri, using an instrument built for high-contrast mid-infrared imaging. Buried in that data was a faint signal, a marginal hint of something at roughly 1 astronomical unit from Alpha Centauri A. They labelled it C1, and then, because they could not be sure of it, they mostly set it aside. Their caution was reasonable, because ground-based telescopes fight a battle that space telescopes never have to. Earth's atmosphere is constantly moving, churning with temperature differences and turbulence, and all that restless air smears and distorts incoming starlight. Astronomers call it seeing, and on even the best night from the best mountaintop, it blurs stellar images and conjures false signals that can masquerade as planets. Adaptive optic systems fight back, flexing mirrors hundreds of times a second to partly cancel the distortion, but they cannot erase it entirely. Ground-based coronagraphy operates at a real disadvantage compared to a telescope floating in the stillness of space, so when C1 appeared as a faint marginal something in the processed images, it could not be cleanly separated from the possibility that it was just a trick of the atmosphere. Most astronomers filed it away as an interesting hint that needed better data, not a discovery. It became a ghost in an old data set, a maybe that nobody could confirm. But after Webb found S1, that ghost suddenly looked very different. Someone asked the question that changes everything. What if C1 and S1 were not two separate maybes, but the same object glimpsed twice 6 years apart, at two different points along the same orbit? A planet on an elongated path would appear at different distances from its star depending on when you happen to look. The 2019 ground signal sat at about 1 astronomical unit. The 2024 Webb signal sat at about 2 astronomical units. If a single world were swinging between those distances on an eccentric orbit, then C1 and S1 might both be real, both be the same planet, each a brief catch of it at a different moment in its journey around Alpha Centauri A. This possibility transformed the problem, because 2 detections constrain an orbit far more tightly than one. A single point tells you almost nothing about a planet's path. 2 points, separated by years, begin to pin it down. The team folded the 2019 position into their orbital modelling alongside the 2024 position, and now the millions of simulated orbits had to satisfy a much stricter set of demands. Any allowed path for S1 had to place it near 1 astronomical unit during the 2019 observation, near 2 astronomical units during August 2024, and then somewhere undetectable during February and April 2025. On top of all that, it still had to remain gravitationally stable for the long haul in the presence of the second star. The computational challenge was enormous. Millions of configurations tested against multiple epochs of seeing and not seeing. But out of that grinding emerged a surprisingly coherent picture. The surviving orbits painted a portrait of a genuinely unusual world. S1 appears to follow a significantly eccentric path, with an eccentricity somewhere around 0.4. To feel what that means, compare it to home. Earth's orbit is very nearly a perfect circle, with an eccentricity of less than 2%. Even Mars, with its noticeably stretched orbit, reaches only about 9%. Mercury, the most eccentric of the major planets, hits about 21%. An eccentricity of 40% is more extreme than anything among our planets, the kind of elongation you usually associate with comets or distant dwarf worlds. On such a path, S1's closest approach to its star would be only about 60% of its farthest distance, a dramatic swing through changing conditions across every single orbit. That orbit takes somewhere between 2 and 3 Earth years to complete, based on the current constraints. At its closest approach, called perihelion, the planet passes within roughly 1 astronomical unit of Alpha Centauri A, about the distance Earth sits from the Sun. At its farthest, called aphelion, it retreats to nearly 2 astronomical units, out toward where Mars would be in our own system. And here is where the whole story snaps into place, because that wide swing is exactly what governs when we can and cannot see it. When S1 approaches perihelion, it moves in too close to the star, into the glare where the coronagraph goes blind, and it effectively hides. When it retreats toward aphelion, it emerges into the sweet spot where Webb can catch its faint warmth. The August 2024 observation apparently caught S1 near aphelion, out in the open. By February and April of 2025, the planet had swung in toward perihelion, into the blind zone. It did not vanish. It simply moved to the part of its orbit where, as a matter of geometry, we are not able to look. There was one more surprise hiding in the numbers, and it is the strangest detail of all. The orbit of S1 appears to be tilted sharply, relative to the plane in which the two bright stars circle each other. Alpha Centauri A and B orbit along a well-determined plane, a planet that formed from the original disk of material around Alpha Centauri A would be expected to share roughly that same plane, the way the planets of our own system all orbit in nearly the same flat sheet they were born from. But as one seems to orbit at something like 50 degrees out of the binary's plane, dramatically tilted, as if it never got the memo about which way the family was supposed to spin. That misalignment is a genuine puzzle. It hints that either S1 formed under unusual conditions, or that something tilted its orbit after it formed, perhaps a close encounter with another planet that was later flung out of the system, or a slow gravitational tug-of-war with the second star pumping the tilt over millions of years. A planet that should be visible and is not, on a path more stretched than a comet's, tilted out of the plane it should have been born into. The more closely the team looked, the stranger and more specific the world became, which is rarely how flukes behave. Flukes are generic. This was particular. And particular is what real things tend to be. The 2019 signal is a reminder that discoveries often wait, unrecognized, in data nobody knew how to read at the time. The Very Large Telescope in Chile had run a dedicated search for planets around Alpha Centauri, using an instrument tuned for high-contrast mid-infrared imaging, and buried in that campaign was a faint something at about 1 astronomical unit from Alpha Centauri A, labelled C1. The trouble was that ground-based telescopes fight a war that space telescopes never face. Earth's atmosphere churns constantly, smearing starlight and conjuring false signals that mimic planets, and although adaptive optic systems flex their mirrors hundreds of times a second to fight back, they cannot fully erase the distortion. C1 was marginal, impossible to cleanly separate from atmospheric mischief, so most astronomers set it aside as an intriguing maybe rather than a discovery. After Webb found S1, that maybe demanded a second look, because of a simple and powerful idea. What if C1 in 2019 and C1 in 2024 were not two separate hints but one planet, caught twice, at two different points along the same orbit? A world on an elongated path appears at different distances depending on when you look, and the 2019 signal at about 1 astronomical unit and the 2024 signal at about 2 astronomical units could be two snapshots of a single object swinging between those distances. Two detections constrain an orbit far better than one, and folding the older position into the modelling forced every allowed path to thread an even tighter set of demands across years of seeing and not seeing. What emerged was a portrait of a genuinely strange world. The surviving orbits favour an eccentricity near 0.4, far more stretched than any major planet in our own system, where Earth's orbit is nearly circular and even Mercury reaches only about 21%. On such a path, S1's closest approach would be only about 60% of its farthest distance, swinging from roughly 1 astronomical unit at perihelion to nearly 2 at aphelion over a period of 2 to 3 years. That swing is exactly what governs when we can see it, hiding it in the glare near perihelion and revealing it near aphelion, which is precisely the pattern the detections and non-detections trace. Stranger still, the orbit appears tilted by something like 50 degrees out of the plane, in which the two stars circle each other, a misalignment that should not happen if the planet simply formed from the disk around its star. Something may have tilted it, a vanished sibling planet flung out long ago, or a slow gravitational tug from the second star pumping the angle over millions of years. A world more stretched than a comet, tilted out of its birthplane, hiding on cue. Flukes are generic. This was specific, and specific is what real things tend to be. The uncertainties are still wide, and it would be dishonest to pretend otherwise. With only a handful of observations, the eccentricity could lie anywhere from about 0.2 to 0.6, the orbital period somewhere between 18 months and 4 years, and the tilt between 30 and 70 degrees, all still compatible with the data. Future observations will narrow those ranges, each new detection or non-detection trimming the allowed family of orbits further. What the team can say with more confidence is that S1, if real, sits in a gravitationally safe zone, staying within about 2 astronomical units of Alpha Centauri A, while the second star keeps its distance, swinging between roughly 11 and 36 astronomical units across its long orbit. That separation is wide enough that the companion never strongly disrupts S1's path, which is why such a planet could survive for billions of years despite the unusual tilt, holding its strange orbit through more time than has passed since the Earth itself was young. The long-term survival of such a world is its own small marvel. A planet on a stretched, tilted orbit inside a binary feels like it should be torn apart, yet detailed calculations suggest S1 could hold its path for billions of years, because it never wanders close enough to the second star for that star's gravity to wreck it. Slow oscillations in its tilt and stretch, the kind binary companions can drive over enormous spans of time, would nudge it without destroying it. It would be a survivor, keeping its strange orbit through more time than has elapsed since life first appeared on Earth. Part 9. A world with 2 suns. Let us for a moment take S1 at its word and assume it is real, because the picture the data paints of it is worth standing inside. Webb did not just catch a dot, it caught enough to begin sketching a portrait, and every number in that portrait points toward a specific kind of world. The light from S1 arrived at a brightness of a few units of flux at 15.5 micrometers. The mid-infrared wavelength Miri was tuned to. That brightness, run through the physics that connects how much heat a thing radiates to how warm it is, yields a temperature centered around 225 Kelvin, roughly 50 degrees below zero on the Celsius scale, cold enough to freeze any earthly thing solid, but warmer than you might expect for a world out at that distance. That warmth is a clue in itself. It is higher than Saturn's cloud-top temperature of about 134 Kelvin and far above Neptune's frigid 55 Kelvin. Part of the difference comes from the star, since Alpha Centauri A pours out about 50% more energy than our Sun and bathes everything around it in correspondingly more light. But part of it comes from within, because gas giants generate their own heat. As such a planet slowly contracts under its own gravity over billions of years, it converts that gravitational energy into warmth that leaks steadily outward, and the decay of heavy elements far inside adds a little more. S1 likely runs on both engines at once, external sunlight and internal fire settling into a temperature that places it between the ice giants of our outer system and the scorching hot Jupiters found roasting against other stars. The mass tells the next part of the story. Working from the brightness and temperature, the team estimated S1 at somewhere around 90 to 150 times the mass of Earth. For comparison, Saturn weighs in at about 95 Earth masses and Jupiter at about 318. So S1 sits squarely in the Saturn class, a substantial gas giant but not a true colossus. Its radius is estimated at roughly 1 to 1 and 1/10 times the radius of Jupiter, meaning it is about as wide as Jupiter while holding less than half the mass. That combination, large size and modest mass, implies a remarkably low density, lower than that of water. Like Saturn, which famously would float if you could find an ocean big enough to drop it in, S1 would be a great puffed-up ball of mostly hydrogen and helium, a lightweight giant built from the primordial gas its system was born in. That low density confirms it formed the way giant planets do, gathering enormous atmospheres of a lightweight gas quickly before the gas of the young system could disperse. We do not yet know what molecules ride in that atmosphere, because catching S1's heat is not the same as splitting its light into a spectrum and reading the chemical fingerprints written there. That kind of analysis waits for future observations, but we can make educated guesses by looking at the gas giants we know. Saturn's atmosphere carries hydrogen, helium, methane, ammonia, and traces of more complex compounds cooked up by sunlight. S1 likely hosts a similar inventory, modified by the somewhat different light of Alpha Centauri A and the warmer temperatures of its closer orbit. There are probably bands of cloud wrapped around it, ammonia ice crystals condensing high in its frigid upper air, storms larger than entire planets churning through its layers, driven by heat rising from below and the uneven warming of its star above. Now let yourself go there, because this is the moment the abstraction becomes a place. Close your eyes and imagine standing somewhere no human has ever been, on the icy surface of a hypothetical moon orbiting S1, 4.5 light-years from home. Your boots rest on frozen ground. Above you hangs a sky no human has seen. The giant planet itself fills a great swathe of that sky, banded in tan and cream and soft orange, its cloud belts sliding slowly past one another, a storm system wider than Earth turning lazily near its equator. And beyond the planet, 2 suns share the sky. The larger one, Alpha Centauri A, hangs yellow-white and familiar, almost exactly the colour of the star you grew up under, because it essentially is the same kind of star. From your position out near 2 astronomical units, it delivers about 1/4 of the light you would feel at noon on Earth, enough to warm your face, noticeably dimmer than an earthly midday but unmistakably sunlight. And then, off to the side, a second sun burns, Alpha Centauri B, a brilliant orange point as bright as the full moon seen from Earth, casting a faint second set of shadows that lie at a slightly different angle than the first, shadows that will slowly shift their direction over the decades as the 2 stars complete their long 80-year dance around one another. 2 suns in one alien sky, doubling every shadow, throwing a strange double twilight across the ice. Science fiction imagined this scene for a century. The data now whispers that somewhere out there, the scene might be real. Hold that image, because it does something important. For most of this story, S1 has been a statistic, a dot, a 5.5 sigma signal, a 52% probability, a number on a screen pulled out of noise by mathematics. But if the numbers are right, the dot is a place. It has weather. It has clouds and storms and a double sunrise. It has perhaps moons, frozen worlds circling it the way our own giants are circled by dozens of icy companions. The whole effort, the decade of failures, the blind leaps across the sky, the millions of simulated orbits, all of it was in service of turning a point of light into a world you could, in principle, stand on. And the strangest thing about that world is not its tilted orbit or its comet-like ellipse or its 2 suns. The strangest thing is how close it is. Of all the places in the universe where 2 suns might hang in an alien sky, this one is the nearest. It is the next house over. It is the porch light, and we may have just seen something standing in its glow. The temperature of S1 is a small number that carries a surprising amount of information. At roughly 225 Kelvin, about 50 degrees below zero on the Celsius scale, it runs warmer than Saturn's cloud tops at 134 Kelvin and far warmer than Neptune's frigid 55. Part of that extra warmth comes from the star, since Alpha Centauri A pours out about half again as much energy as our Sun. But part of it comes from within, because giant planets are not merely heated from outside. As they slowly contract under their own gravity across billions of years, they convert that gravitational energy into heat that leaks steadily outward, with the decay of heavy elements adding a little more. S1 likely burns on both engines, sunlight from without, and a slow fire from within, settling into a temperature that places it between the ice giants of our outer system and the searing hot Jupiters found roasting against other stars. The mass and size sketch the rest of the body. At somewhere between 90 and 150 Earth masses, S1 sits in the Saturn class, since Saturn itself weighs about 95 Earth masses, while Jupiter weighs about 318. Its radius of roughly 1 Jupiter width, paired with that modest mass, implies a density lower than water, the same featherweight quality that would let Saturn float if you could find an ocean large enough. That low density marks it as a true gas giant, a puffed-up sphere of mostly hydrogen and helium gathered quickly from the gas of its young system. We cannot yet read the specific molecules in its air, since catching its heat is not the same as splitting its light into a spectrum, but by analogy to Saturn we can expect hydrogen, helium, methane, ammonia, and traces of more complex compounds wrapped in cloud bands and stirred by storms larger than entire planets. What all of this earns is the right to imagine the place rather than the number. Stand again on that hypothetical moon, ice underfoot, the banded giant filling a great arc of the sky, its cloud belts sliding slowly past one another. The larger sun, yellow-white and familiar, delivers about a quarter of Earth's noon light from 2 astronomical units out, enough to warm your face. The smaller orange sun burns off to one side as bright as our full moon, laying down a second faint set of shadows angled differently from the first, shadows that will drift over decades as the 2 stars complete their long dance. For most of this story, S1 has been a dot, a probability, a signal dug out of noise. But if the numbers hold, the dot is a place with weather and a double sunrise, and the most remarkable thing about it is simply that of all the worlds where 2 suns might hang in an alien sky, this one is the nearest. What makes a confirmed S1 so valuable is that its eccentric orbit would turn it into a natural laboratory. As the planet swings from its closer approach to its farther retreat, the amount of starlight it receives changes substantially across each orbit, which should drive measurable shifts in its temperature, its weather, and the chemistry of its air. By watching how its faint glow varies through those phases, future observations could read the structure of its atmosphere in a way that single snapshots of more distant worlds never allow. And because the star is so nearly a copy of the sun, whatever we learned would apply, more directly than anything before, to the question of how a mature world behaves under the kind of light that warms us. No other known planet offers that combination of nearness, age, and sun-like illumination, which is why a single confirmed dot would be worth years of telescope time and careful study. The greatest prize, if moons exist, would not be the gas giant but its satellites, and reading them would take instruments beyond even Webb. We cannot resolve a moon beside S1 today, but the giant telescopes now rising, and future observatories designed to image small worlds, may one day separate a large moon from its planet and search its air for the chemical signatures of life. A gas giant is uninhabitable, but a warm moon in a sun-like temperate zone is one of the more plausible places to look for biology within reach, which turns a planet that cannot host life into a possible gateway to it. Part 10. Moons, Water, and the Company We Might Keep. A Saturn-sized ball of hydrogen and helium cannot by itself host life as we understand it. C1 has no solid surface where anything could stand, no ocean where chemistry could pool, only an atmosphere thickening downward into crushing pressures and temperatures that would destroy any earthly thing. As a place to look for living things, the planet itself is a dead end. But giant planets almost never travel alone, and that single fact reopens the entire question in a way that is hard to stop thinking about once you have started. Consider our own giants. Saturn carries more than 270 known moons, a number that keeps climbing as our instruments improve. Jupiter holds dozens of its own. These are not all barren rocks. Saturn's largest moon, Titan, is bigger than the planet Mercury, and wears a thick nitrogen atmosphere denser than Earth's, with rivers and seas of liquid methane carving its frozen surface and a slow, patient organic chemistry running beneath an orange haze. Saturn's small moon, Enceladus, hides a global ocean of liquid water beneath its icy shell, and it sprays that water into space through cracks near its south pole, a buried sea announcing itself to anyone watching. Jupiter's moon, Europa, conceals an ocean estimated to be many tens of kilometers below its ice, kept liquid by the constant flexing of Jupiter's gravity, with the real possibility of chemical energy at its dark sea floor. Ganymede and Callisto likely hold buried water layers of their own. We have, in our own backyard, a whole collection of ocean worlds, kept warm not by sunlight but by tides. Now place a moon system like that around S1 and change one crucial thing. The moons of Jupiter and Saturn are frozen because they orbit far from the Sun in the cold outer reaches of our system, surviving on internal heat alone. But as one orbits within the temperate zone of Alpha Centauri A, the band of distances where a world receives enough starlight that liquid water could persist on a surface, a moon orbiting S1 would be warmed not only by tides, but by genuine sun-like sunlight. Imagine a world like Titan, with its rivers and seas and thick sheltering atmosphere, but warm enough that those rivers ran with water instead of methane. Imagine familiar cycles of evaporation and rain, lakes under a double sun, a chemistry that might run along lines an earthly biologist could almost recognize. We cannot see such a moon. The separation between S1 and any satellite would be far too small for any current telescope to resolve from this distance. But everything we understand about how planets and moons form says that if S1 is real, it should have moons, and some of those moons might sit in exactly the conditions where life, as a possibility, cannot be ruled out. There is even a piece of evidence that nudges this from idle dreaming towards something more grounded, and it came out of the very same observations that found S1. While measuring the system, Webb also constrained the amount of dust around Alpha Centauri A, the fine debris produced by colliding asteroids and crumbling comets, what astronomers call exozodiacal dust, after the faint zodiacal glow that fills our own inner solar system. A system choked with such dust would be a hostile place, a sign of frequent violent collisions, ongoing bombardment, the kind of chaos that batters young worlds and snuffs out fragile biospheres before they can take hold. Webb found that the dust around Alpha Centauri A is low, only about 5 to 8 times the level in our own system, which is the most sensitive such measurement ever made around any star other than the Sun, an order of magnitude finer than any previous limit. A low-dust system is a calm system, a mature one that has settled into a kind of equilibrium after billions of years, the sort of place where worlds are not constantly being pummeled. It is, in other words, encouraging news for anything trying to live there. The discovery reaches even further than this one system, because it quietly overturns a long-standing prejudice. For decades, binary star systems were considered hostile to planets. The reasoning seemed sound. 2 stars locked in a close gravitational dance should stir and strip the disk of material around them before planets could ever coalesce, and computer simulations consistently predicted that planet formation would be suppressed or prevented entirely in tight pairs like Alpha Centauri. Only narrow zones, close to one star or the other, looked even marginally stable. And yet S1 appears to sit in exactly that marginal band, threading the needle between the region too close to the star for us to see, and the region too far out for an orbit to survive the second star's pull. A planet exists, it seems, precisely where theory said one might just barely hang on. If planets can form and survive here, around a tight binary that should have been hostile, then a huge population of stars previously written off becomes fair game. The numbers that follow from that are staggering in the best way. Our galaxy holds something like 200 billion stars. Roughly half of all Sun-like stars live in binary or multiple systems rather than alone. If planets can survive around binaries like Alpha Centauri, then perhaps 100 billion binary systems across the Milky Way could host worlds of their own. Even if only 1 in 10 of them does, that is 10 billion additional planets, orbiting paired stars that we had quietly assumed were empty. Some fraction of those would sit in temperate zones. The galaxy's accounting of potentially habitable real estate does not just inch upward with this discovery, it potentially doubles. Frank Drake's famous equation for estimating how many worlds might host life multiplies together a chain of factors, and one of those factors is simply the fraction of stars with planets. Thanks to thousands of exoplanet discoveries, we already knew that fraction was close to 1, that planets are nearly everywhere. Finding them around binaries pushes that abundance into places we had excluded, and makes the universe feel a little more crowded with possibility than it did before. And then there is the part that turns all this from astronomy into something closer to a destination. 4.5 light years is an enormous distance, but it is not an impossible one. Initiatives like Breakthrough Starshot have proposed launching tiny gram-scale spacecraft toward Alpha Centauri at a fifth of the speed of light, pushed by enormous ground-based lasers, probes that could reach our nearest neighbour in roughly 2 decades of flight and send back close-up observations within a single human lifetime. For years, that idea had a hollow centre, because why pour billions into a journey to a system that might be completely empty? Knowing that a planet likely waits there changes the entire calculation. It gives the dreamers a target with an address. The cosmic front porch is no longer just a poetic phrase for the nearest star. It is a porch with a light on, and possibly someone, or at least somewhere, home. Long before any probe departs, a new generation of giant telescopes now under construction, with mirrors 30 meters wide and larger, will turn their gaze toward Alpha Centauri and see it far more clearly than Webb ever could, refining S1's orbit, hunting for smaller worlds, and perhaps one day reading the very air of a distant moon. The neighbourhood we once thought unknowable is becoming a place we can study, and maybe eventually a place we can visit. The ocean worlds of our own system are the reason a gas giant in a temperate zone is so much more than a curiosity. Saturn's Titan wears an atmosphere thicker than Earth's, and runs rivers and seas of liquid methane across a frozen surface, with a slow, organic chemistry working beneath its haze. Its small sibling Enceladus hides a global ocean of liquid water under its ice, and sprays that water into space through cracks near its south pole, announcing a buried sea to anyone watching. Jupiter's Europa holds an ocean tens of kilometers below its shell, kept liquid by the constant flexing of Jupiter's gravity, and Ganymede and Callisto likely carry buried water of their own. We already have a small collection of ocean worlds next door, kept warm not by sunlight but by tides. Now change the one variable that matters and place such moons around S1. The moons of our giants are frozen because they orbit far from the Sun, but S1 sits inside the temperate zone of Alpha Centauri A, where a world receives enough starlight for liquid water to survive on a surface. A moon there would be warmed by both tides and genuine sun-like light, and you could imagine a Titan-like world whose rivers ran with water instead of methane, with familiar cycles of rain and evaporation under a double sun. We cannot resolve such a moon from here, but everything we know about how planets and moons form says that if S1 exists, it should have a family of them, and some could sit in exactly the conditions where life cannot be ruled out. The low dust around the system, only about 5 to 8 times our own, and the most sensitive such measurement ever made around another star, hints at a calm, mature place rather than one being battered by constant collisions, which is encouraging for anything trying to take hold there. The discovery quietly overturns an old prejudice as well. Since binary systems were long thought hostile to planets, their disks stirred and stripped before worlds could form. Yet one appears to occupy exactly the narrow band of stability that theory grudgingly allowed, threading between the region too close to the star to see and the region too far to survive the second star's pull. If planets can hold on here, around a tight binary, then a huge population of stars we had written off becomes fair game. Our galaxy holds about 200 billion stars, roughly half of the Sun-like ones in pairs, so even modest planet odds imply something like 10 billion worlds around binaries, a number that effectively doubles the galaxy's potentially habitable accounting, and pushes one whole term of Drake's old equation upward. And 4.5 light years is not an impossible distance. Projects like Breakthrough Starshot imagine tiny probes pushed by ground-based lasers to a fifth of light speed, able to reach Alpha Centauri within a couple of decades, while giant telescopes now rising, with mirrors 30 meters wide and larger, prepare to study the system far more sharply than Webb ever could. The cosmic front porch is no longer just a phrase for the nearest star. It is a porch with a light on, and possibly somewhere, home. The pull of an actual destination is hard to overstate because it changes how people build. For years, proposals to send probes toward another star sounded almost like poetry. beautiful and weightless, because nobody knew whether there was anything worth visiting. A confirmed planet hands the dreamers a target with an address, and engineers work very differently when they know exactly what they are aiming at. A probe travelling at a fifth of the speed of light could cross the 4.5 light-years in roughly 2 decades, sending its findings home within a single human lifetime, and that math stops being idle the moment there is a world at the far end. Beyond the probes, the next generation of giant ground telescopes and dedicated future space observatories built to image worlds like our own will turn toward this system first, because it is the closest and therefore the most rewarding. Alpha Centauri is becoming not a fantasy but a frontier, the first place we will truly learn how to study and perhaps one day how to reach. The techniques born from this struggle will not stay at Alpha Centauri. The blind offset, the reference subtraction, the patient peeling back of noise, all of it transfers to other nearby stars that once seemed too hard. Tau Ceti, about 12 light-years away, is a sun-like star already suspected of hosting worlds. Epsilon Eridani, around 10.5 light-years off, is younger and ringed with debris. Other nearby systems, some of them binaries much like this one, wait their turn. Each is a fresh chance to apply what Alpha Centauri taught us, which means this one brutal target may end up opening a whole neighbourhood of stars to direct study. Part 11. The verdict awaiting delivery. Everything now points toward a single date on a telescope calendar. The orbital models that survived all that testing make a specific prediction, and it is the kind of prediction that turns a mystery into a countdown. If S1 is real and travels along the family of stable orbits consistent with every detection and non-detection so far, then it should swing back out toward aphelion, back into the region where Webb's coronagraph can see it, in the second half of 2026. August of that year stands out as the most probable window for the planet to reappear. The team has effectively told the universe where and when to show its hand, and now everyone waits to see whether it will. Think about what hangs on that window. If Webb looks at Alpha Centauri A in August 2026 and finds S1 sitting near its predicted position, the case for a real planet becomes overwhelming. There would then be 3 detections spread across 7 years, the faint 2019 hint from the ground, the strong 2024 detection from space, and a 2026 confirmation, all falling along a single consistent orbit. No statistical fluke could produce a pattern that's coherent across multiple instruments and multiple years. No background object could mimic an orbit that closes so neatly. A third detection at the right place would essentially prove that a world circles our nearest sun-like neighbour, and the long search would finally have its answer. And if S1 does not appear, even with the geometry favourable, then the mystery only grows. Either the orbit is stranger than the models allow, hiding the planet longer than expected, or the original 2024 detection truly was that 1 in 10 million ghost after all, a signal that fooled every test. Either way, we learn something real. Confirmation would open the door to studying our nearest planetary neighbour in detail. A failure would sharpen the techniques and rule out a candidate, which is its own kind of progress. Science moves forward on both kinds of nights. It is worth pausing on just how much would change if S1 holds up, because the superlatives stack into something almost dizzying. It would be the closest exoplanet to Earth, orbiting in the temperate zone of a sun-like star. It would be the nearest directly imaged exoplanet by a wide margin, since every other directly photographed world circles a star at least 10 times farther away. It would be the oldest directly imaged planet by an enormous factor, billions of years old rather than the tens of millions typical of the young hot worlds we usually catch. It would be the coldest directly imaged planet, opening up a whole population of mature, cool worlds that have been invisible to us until now. And it would orbit closer to its star than any directly imaged planet before it. Each of those firsts is a doorway into science we have never been able to do. The chance to study a settled, sunlit world at an age and a distance that finally resemble our own circumstances rather than some exotic outlier. but step back from the single candidate, because the larger truth does not depend on whether this particular dot survives. Webb has already broken something that stayed unbroken through all of human history. It has shown that the planetary system of Alpha Centauri can be explored from here. The barrier that hid our nearest neighbour behind its own glare for 70 years, the searchlight that drowned every firefly beside it, has been beaten, at least once, by enough ingenuity and stubbornness to pull a real signal out of an impossible target. Whether S1 is confirmed or fades, that door does not close again. Direct imaging of mature planets around sun-like stars at tiny separations is now a thing we know how to attempt, and the methods built for this one brutal target, the blind leaps across the sky, the reference subtraction, the patient peeling back of noise, carry directly to other nearby stars waiting their turn. Let yourself end where this kind of story should end, out in the dark between the stars. Somewhere in the 4.5 light years between here and Alpha Centauri, light is already travelling toward us that will carry the answer. If S1 is out there right now, swinging back toward aphelion, then the photons that will reveal it in 2026 have either already left that system or are leaving it as you listen, streaming across the emptiness at the only speed the universe allows, indifferent to our waiting. The verdict is, in a real sense, already sealed. Out there, the planet either exists or it does not. It is either tracing its long, tilted ellipse around that yellow-white star or it is not, and nothing we do between now and August 2026 changes which is true. The universe already knows the answer. It has known all along. We are simply standing in the dark at the near end of a 4.5-year-long beam of light, waiting for the part of the answer that is still in transit to finally arrive. There is a particular kind of comfort in that, and it is the note worth carrying off to sleep. For all of human history, the question of whether our nearest neighbour had worlds of its own was a question we could only wonder about, a blank we filled with stories. Now it is a question with a due date. The firefly beside the searchlight has been photographed at least once, and we have learned how to wait for it to show itself again. The closest sun-like star to Earth no longer keeps perfect privacy. Its planets, whether one or many, whether confirmed tomorrow or still hiding, have begun to emerge from the glare that hid them since the first human being looked up at that point of light and wondered. A gas giant may circle in the warm zone of our nearest neighbour. Moons may turn around it where water could pool beneath a double sunrise. Life may have found a foothold there, or the whole system may be barren and still. Either answer is worth everything it took to ask, and whatever the light carries when it finally arrives, the loneliness of being the only world that ever wondered grows a little less certain with every faint dot we manage to pull out of the dark. The prediction for 2026 is precise enough to feel like a countdown, and that precision is itself a kind of confidence. If S1 is real and follows the family of stable orbits the data allows, it should swing back out toward aphelion and into Webb's detectable ring in the second half of the year, with August standing out as the most probable window. The team has, in effect, told the universe where and when to show its hand. A detection at the predicted spot would join the 2019 ground hint and the 2024 space detection into 3 points across 7 years, falling along one consistent orbit, a pattern no fluke and no background object could fake. The case would tip from compelling to overwhelming. It is worth holding the stakes of confirmation, because they pile into something almost hard to believe. A confirmed S1 would be the closest exoplanet in the temperate zone of a sun-like star, the nearest directly imaged planet by a wide margin, the oldest such planet by a factor of hundreds, the coldest, and the closest in to its star of any we have imaged. Each of those firsts is a doorway into science we've never been able to attempt, the chance to study a mature, sunlit world at an age and distance that finally resemble our own, rather than some exotic young outlier. And even a non-detection would teach us something real, either revising the orbit or retiring the candidate, both of which sharpen the methods for the searches to come. Science moves forward on both kinds of nights, but the largest truth does not hang on this one dot at all. Webb has already broken a barrier that held through all of human history, proving that the planetary system of our nearest neighbour can be studied from here, that the searchlight which drowned every firefly beside it can be beaten by enough patience and ingenuity to pull a real signal from an impossible target. Whether as one is confirmed or fades, that door stays open, and the methods built for this brutal star carry to the next ones in line. So let the story end out in the dark, where it belongs. Somewhere in the 4.5 light years between here and Alpha Centauri, light is already on its way that will carry the answer, photons that left that system as you listen, crossing the emptiness at the only speed the universe permits, indifferent to our waiting. The verdict is already sealed out there. The planet either traces its long tilted ellipse around that yellow-white star tonight, or it does not, and nothing we do changes which is true. The universe already knows the answer. It has always known. We are simply standing at the near end of a 4.5-year beam of light, waiting for the part still in transit to arrive. The firefly beside the searchlight has been photographed at least once, and we have learned how to wait for it to glow again. The nearest twin of our sun no longer keeps perfect privacy, and the old loneliness of being the only world that ever wondered grows a little less certain with every faint dot we manage to lift out of the dark. There is a quiet shift in how we stand toward the universe once a single nearby star stops being anonymous. For most of history, the stars were unreachable lights, beautiful and remote, a backdrop to human life rather than a set of places. Then we learned they were other suns, and later that those suns held worlds. But the knowledge stayed abstract, a matter of statistics spread across an unimaginable distance. A specific planet around a specific neighbour changes that. It makes us less like spectators cataloguing anonymous lights, and more like residents of a neighbourhood, with a particular house next door and a particular light burning on its porch. The 4.5 light years do not shrink, and the journey stays beyond our current reach, but the gulf turns from something endless in practice into something merely large in principle, a problem of engineering rather than a wall against knowing. That is the gift hidden inside one faint stubborn dot, and it is worth carrying gently into sleep. The oldest question about our nearest neighbour now has a due date, and whatever the light finally tells us, we are no longer entirely alone in our wondering. So we wait, and waiting, it turns out, is a kind of knowing too. The light that will settle the question is already on its way, and there is nothing left to do but let it arrive. Whatever it carries, the asking has already changed us, because a question that was open for all of human history now has a date attached to its answer. That is the thought to drift off on tonight, unhurried and unafraid. Somewhere out there a faint world may be tracing its long, slow ellipse around a star almost exactly like our own, and for the first time we know how to wait for it to show itself again.